Okay, so let's go for tutorials. And for tutorials, if you just give a look into the canvas, you will see that I uploaded 3 IPython notebook files and the 2 data sets which we are going to play with. So now what you need to do, you need to download them. And yes, you just put them into the folder, the same folder as the IPython notebooks, and run it in a Jupyter. Okay, so everybody is happy with the Jupyter. I don't see any reactions in the chat. Okay, so is everybody back? That's the first question, because I don't see any reaction on the Jupyter request. Okay, I get 1, 2, okay. Okay, good. Okay, so again, go to the canvas and download the Jupyter notebooks and the 2 CSV file, and run the Jupyter notebooks from the same folder as our playing around data sets. Okay. Yeah, Spider is also fine, but the Spider will have a difficulty with opening my Jupyter notebooks. So if you are more comfortable with Spider, you will need to open it in Jupyter, convert it to the Py file, and open it in Spider. That is also fine. Okay, so the first notebook is the simplest. Where is exactly the Jupyter file? The Jupyter files are in Canvas, week 2. So if you look into the week 2, in the same place where the notes were for today's lecture, now there is 3 Jupyter files and the 2 CSV files. Mm-hmm. Okay. Mubarak is writing that he can see only PDF file. Okay. Anybody, participants, are you all seeing only the PDF file? Yeah, refresh the page. That usually helps. Or you can log out and log in into the canvas, or at least refreshing the page should help. Okay. Okay. Are we all good to go? Okay, good. So, and the first kind of the data set which we are going to be analyzed is we're going to do a very, very naive kind of linear regression with violation all the fancy rules which I just was telling you for the half of the day. But in this particular case, it's working. Why not? But you might want to apply some of them. So, and the file is called, if you open it, linear regression on US housing prices, where there is a data set, which is also was in the canvas, yes, that you saw housing.csv file. So, and what we need, yes, kind of like it doesn't use any L norms, kind of penalties. It doesn't use any normalizations. It's just, out of the box, and one can see how far we can go. And, as one of the extra tasks for you, it will be, yes, to make it work nicer by using some extra tricks, which I told you, which you can do within this framework. Okay, so what you need to load NumPy. NumPy is a package. I mean, we're not going to use it explicitly. It's a package of dealing with linear algebra, but just in case if we need it, pandas, which you all seen last week, I assume, matplotlib, pyplot, and there is a specific special package for the data science, so kind of for visualizing the data. It's called Seaborn, and one shouldn't be kind of afraid. It just, for the data science, it allows you to do things a little bit nicer than matplotlib, in the sense like less lines of code, but the logic is the same. Okay, so you run it, and okay, you need to open the first one linear regression practice. Okay, and after we imported libraries which we need, we can import the CSV file with the kind of with our original data into the pandas data frame. Yes, and I assume you've seen it last week, so it shouldn't be too surprising to you. And what are we dealing with? We're dealing with a table. We can add a little bit more lines. So we're dealing with a table which have the following data. Yes, there is an average area income, average area house age, average area number of rooms, average area number of bedrooms, area population, and the price and address. So an address is, for this kind of analysis, which we are going to do, will be irrelevant feature. Yes, because we are not going to process address in any meaningful way. While, of course, one can do that as well, because one can use some geotagging to connect the addresses which are in one neighborhood, and that could provide you extra information. But this is not the point for what we're going to do. Matplotlib inline with a percentage sign is making sure that it will reflect it will reflect the figures inside of the Jupyter notebook nicely. Okay, so we can check the info. Yes, and that's what usually you need to do, because you want to see is that we're dealing with 5,000 entries, yeah, and they're all non-null. So it's mean that they are all fields, so we don't have empty values. Yes, kind of all of them are numbers, real numbers, except the last one, which is address. And addressed is an object, which is, we see that it's a special probably type of string or whatever. But for us, it doesn't matter, because we're just going to ignore it. Okay, so, and in the moment when we see that, we don't have missing data, so everywhere the data is put in, yes, kind of non-null count. So we get that everything is there. So we can give a look, we can do the data framed describe. So just to see what are we dealing with. And here we just pass in the extra parameter with the percentiles. Usually it's only 0.25, 0.5, and 0.75. In this example, it's a little bit more. So 10%, of the 10%, 25%, 50, 75, and 90% of the data. What would be the the means of for those quantities? So we have count 5,000 entries. We could have an average value, standard deviation, minimum, maximum, and the corresponding percentile values. Okay. First file is not opening. In order to open it, you need to have Jupyter processing thing installed. The easiest version is Anaconda. Do you know what the Anaconda is? Do you need the link? Yeah, let me just quickly find the Anaconda. Okay, and there is a 3 replies into that. Okay, yeah, there is a good enough answer. So one can use a Jupyter Notebook or Jupyter Lab. They both works fine. You're supposed to open this file, one linear regression practice. This file. You just don't click on the link because the link wouldn't work. So this file. Okay, let's keep going. Okay, so we have our columns. We have some information about them, and first what we might want to do. Yes, kind of like first we can give a look on the columns. Yes, DF columns will give us list of columns. And what we can do using this Seaborn, if we just do a Seaborn pair plot DF, we do pair plot of data frame. What it will do? It will do exactly what was on my screen, but now I just rerun it. So what we get the kind of correlation matrix, or not kind of, but the correlation matrix of all numerical fields with each other. Yes, so kind of average area income with average area income is just, a very nice normal distribution, and average area income with average area house age doesn't seem to be correlated at all. Yeah, it's like it's a circle. Average area number of rooms, also not really correlated. Average area number of bedrooms and average area income also does not seem to be correlated, because for every number of bedrooms, there is kind of like wide range of options. And there is only one correlation, which we can say that, okay, something could be there. So average area income and price. So you see, it's not perfect circle. It's more like something elongated, which is meaning that, yeah, as the average area income grows, the price is also growing. And we can see very similar correlation with most of the rest parameters, except the average number of bedrooms, because if it's tilted, not too much, but at least you can get a little information, kind of a very basic information about how are your correlations in your data set by default without doing anything. How related to each other the entries which you have. Okay. So we can also use some plotting characteristics to see, for example, see what is the distribution of the price in forms of the histogram. But this is just to show you the abilities and number of bins. You specify the number of bins, and it's plotting with the number of bins. If you change the number of bins, obviously, you'll get a more coarse histogram, or if you increase the number of bins, you get a nicer histogram, or more fine-grained histogram. So, yeah, we can plot kind of the values as a density, but I'm sure that these kind of things you probably seen last week. Okay, so DEF correlations will calculate the correlations between the numerical fields of the data set. Yeah, and we can also, what we can do, because now these correlations are calculated. Oops. I'm getting the same diagram, but again. Okay, first of all, it's not an error, it's a warning, yeah? So maybe, okay, so I don't have such a warning, and I'm not sure, maybe it's related to the size of your screen, because when it's tight, it means that, it's more compressed, and I'm not suppressing the warnings. But warnings usually you can ignore, because as you see, there will be also some other warnings coming. And the another one is, name DF is not defined, meaning that you haven't loaded the data set. So make sure that you are loading in this line of code: df, pd read csv, and file, and df head. If you don't see, I mean, if you haven't read the data set, this cell will also give you trouble. Okay. Okay, yeah, I see. So it's here, yes. Thank you. Okay. Okay, good. So, wait. Okay, so now we can calculate the correlation of the numeric only fields, and we can plot it as a heat map. Yeah, kind of like with the following legend, yes. So from 0 to 1, and we have obviously columns with itself are perfectly correlated, but you see what we exactly have seen, that, average area income and the price are quite correlated. Average area house age, we see that, there are some correlations, but the smaller ones, and some things, some fields are even negatively correlated, but quite weakly. Okay. Yeah, SNS is not defined means that you need to import Seaborn or you need to install it if it's not installed. So this one, this cell, okay. So now we need to do the separation to the features. For that, we need to take columns. It's good to calculate this length because, what is our columns? Where is the list of our columns? Just now here. I know. Yes, here is our list of columns. And the features are, which we're going to use, will be the first 5 columns. Price is a target, and address we neglect in this model. Okay, so it means that for the X, we need the first 5 column. For the Y, we need for the Y, we need 5 column number 6. Yes, I did number 5 because it's from 0, and the column number 7 we ignore. Okay, so that's how we can do it. So first of all, we get a total list of columns, and X is we're cutting out all the columns from 0 to 5. Y, we're getting the last column, and we can check that we have a proper shape of these 2 resulting sub-data sets. Yes, so that we have 5,000 by 5, and just the 5,000 entries for the Ys. We're all good. Okay. So, and the only thing which we're going to do out of what I told you is we're going to do the test train split. So we don't need to do it manually. We can do it using the standard scikit-learn tools. What we need to do, have I run that? I was just talking about that. Okay, now I run it. Okay, so we need to load test train split from scikit-learn model selection. And what we need to do now, we need to decide how much test and train we want to have as a split. In this example, I use one kind of 30% as a test and 70% as a train. So, and the typical, the typical way how you can define it is you write X train, X test, Y train, Y test is equal to this function, test train split. Here is our all X's, all Y's. We're saying that, you need to cut 30% for the test. And we also need to indicate some, we might want to indicate the random state for reproducibility, which is going to use to generate kind of this random split. But we don't have to. But in that case, if we don't indicate here random state, in that case, every time we do the test train split of one and the same code, it's going to be different splits. I mean, different X's and Y's. Okay, so we can check the shapes of the resulting data so that we know that we are on the right track and the code is doing exactly what we want. Yeah, so that we have the size of the training set, 3,500 record of the 5 columns. Test is 1,500, 5 columns. Yes, Y, 3,500 by 1. and the test is 1,500 by 1. Very good. So, and can you explain random state variable and why it is 42? 42 is because it's it's the answer for the what is called the most important question in the universe. And we just, if we don't do the random state here, what it will do, because when it's do test and training split, you need to take a random x's and corresponding y's. So if we don't do a random state here, so if I run test train split once, I will get, some distribution of train and test data. Without fixing random state, I run it again, and I will get the different x's and y's. And one might think that this is okay, and this is in principle, it's okay. But what will be the thing is that, if I have a random distribution of training and test, I can get one precision, but when you will run your code, you might get a slightly different precision, which might be related to the fact that, some x's and some x's swapped between the training and test, so that, that you obtain exactly the same results as I am obtaining. That's why I'm fixing the random state, which is fixing the pseudo-random generator, which is going to do the splitting. So that when you will run the code, you're supposed to obtain exactly the same result. If you remove this bit, and you're welcome to try to do it as an experiment, your precision of your training might slightly vary from what I achieve, or kind of what I get. But, it's just, if I want that my code is fully reproducible, I need also to fix the random numbers which I'm using. So that's the only reason. Why it's 42? There is no if it says that the x is not defined, it means that you haven't defined x. That it means that you haven't run this cell and you haven't obtained the positive results. Okay. I'm not sure what the question is. Just like a lecture, not a practical. I'm okay? That I'm not sure. What do you mean? Can you please specify it? But can you explain why in this case we only split train and test and not validation? You will see why, because why we need the validation. We need the validation if we need to train a hyperparameter. But here we're just going to do a vanilla linear regression without hyperparameters, without regularization, without anything. So it's going just to be, it's the most naive and the most brute force way of doing things. In the next notebook, we're going to do splits with validation, and we're going to do splits with, crossfold, and we're going to do a little bit of optimization of the parameters or search for the parameters. But here it's just, it might happen so that, you are dealing with a data science problem, which is so simple that the most wrong things which you can do, they're still working and working pretty well. So, and that's the idea. I think this I just answered, why we're not split into the test, train, and validation. Yes, because we just split into the test and train. And when we are going to have a validation, this is going to be done by some other function of the scikit-learn, and it's going to be kind of, it's coming. Don't worry, validation is coming. And if you want to know whether this function can do it or not, you can always do scikit-learn Yes, and what we'll see that essentially, yes, kind of like that's the only thing which this function can do. It can only split into the two subsets. Nobody prevent you taking training data and resplit it again and separate validation separately if you need. But as I mentioned, here we just don't need it. Line 17. What is line? This one. Yes. Okay. So in order to understand line 17, let's do a very simple thing. Let's add one more cell and just let's give a look. What is the L column we've seen? So what is this? This is the list with the names of the columns. Ah, sorry. Okay, good. So, but now the thing is that what I'm doing, I'm slicing this list and I'm cutting out from this list some entries. So what do I need to do? I mean, in principle, what I could have done, I could have said that, okay, I want from this list, yes, if I write, L column 0, I will get the first entry of the list. L column 1, I'll get a second entry of the list and so on, yes, until the end, L column 6 will give me address, and that would be all columns. But now the question is, and in principle, if we want, yes, area population is the last one, which in principle we could have created the list of all entries by doing it manually, just and do something like this, but you already see that it's magically inefficient. Yeah, especially you imagine that if you have kind of and we just get, so what we achieve by doing this, we get a list of the names of the columns which we need for our kind of for our input data. But doing this, as you see, it's really inefficient in the sense of doing it kind of like, if you have more columns, we could have been doing it till tomorrow. And in order to do it in a little bit more efficient way, we can use the fact that when we're dealing with the arrays, or kind of when we're dealing with the strings, we can do the operation which is called slicing. And I don't know, do you have that or not? But, kind of like, if we just write something like this, it will be the full list. Here, I indicate from where we start and nothing is changing. And if I put here 6, so it's up to, so it's the way how to define the range. So, okay, if I put up to the 7, I get the full list. But if now I will reduce the range, it will tell me up to which kind of like select from this list all the entries for the indexes from 0 to n-1, where this is kind of where this is the last guy. Okay, so but in order to do it again in a fancy way, we know what is the length, what is the number of features, and that's why we're doing it like this. Because this is number of features is 7, so that's exactly the same 5. But when we do it like that, we get it in a little bit more generalizable way. So, if you have 20 columns, you don't need to write, recount it. It's just, you know that the last 2 columns are the columns which you want to ignore. Because in our case, the last column is address, which we ignore completely. And the pre-last column is price, which we need for the Ys. And when we have something like this, now when we say to the data frame, select to me only this list of columns, it's going to create to you a subset of the data frame. You see, here is when I write X head, which only contains these columns. I assume that the last week in your pandas, you should have seen things like this. So the slicing of the columns and the slicing of the rows. Okay, and here, the y, we're just saying, okay, give me the column with the index, which correspond to the index of the price column. Okay, so by doing this, we just kind of out of where I have the table. Now, where is the table? Okay, by doing that, we manage out of this table, cut only first columns by ignoring the last two, and the cut this column for the y. So x's will be these guys, or these guys, and the y is the price. Is it better? Okay. So if it was, I mean, you could in principle do it. Probably, you know, when you've been taught, you've been shown as I've shown you in the beginning, so that when you explicitly indicate the list. But you know, when you have a list of columns which is kind of going one after each other, it's much better to do it like this, because you know, if you have 20 columns, it will be more involved to do a list of the 20 entries. So if you have 100 columns, it will be even more difficult. That's why, you know, how you organize your columns in your data is also a parameter which can simplify you or make your life a little bit more difficult. Okay, so let's go back to the cells. Okay. So those of one who don't like random state 42, you can put random state 2024, or you can just remove this line at all. But in that case, you might get a slightly different performance. Okay. Okay, so now, yes, you need to run all the cells one after the other. Now we're coming to finally to the choosing our vanilla model, or very simple model. We're going out of the family scikit-learn linear model, choose linear regression. And again, one can check how this world is looking like in the scikit-learn. What are the options? If we just go in the scikit-learn linear model, we're going to see that there are several linear models which one can consider, and they are all on this side. Yes, so kind of we have a ordinary least squares and so on. And you're going to see what is the ridge regression, what is the difference between the ridge regression and what is the lasso, and so on and so forth. Okay, so far we need only linear regression, and we need, of course, metrics to measure how good or how bad are we doing. So we just run the cell, and we're saying, okay, now we're creating model. So we're saying that LM will be our linear regression model. And again, if we just go into the linear models, where is my linear regression? Oh, this is the kind of explanation theory. This is not what I wanted to show you, sorry. Because I wanted to show you, yes, let's go here. Yes, so I want to show you the function, yes? So, and we can see the list of input data, which we need in order to kind of the input parameters for the function. And we just, all the models, they have essentially in scikit-learn one and the same language. So it's model fit, and you do train, X train, Y train. And when we do that, what happens under the hood, the kind of the gradient descent have been applied and the model have been trained. And now we can give a look how the model is behaving. So for example, we can give a look, what is the value of the intercept term? And you see it's large and negative number of free term. and we can get the coefficients in front of each column. So this is your beta 0, beta 1, beta 2, beta 3, and beta 4. So we can push it into a little data frame just to have it looks a little bit nicer. And now, before we even continue, so we get these coefficients beta, and I have a stupid question to you. Does the fact that coefficient in front of the average area house age is largest, does it mean that it's the most important coefficient? And the fact that the area population have the smallest coefficient doesn't imply that it's least important coefficient. Okay, I get to know. I'm not sure that what does it mean? It's just a measure? It's just a measure of what? In principle, it should. But in this particular case, no, because we haven't done one thing with you. We haven't normalized the data. And if you give a look on the entries, yeah, kind of like average area income is the real number with the 5 digits. Average house age is a 1-digit number. Average area is a 1-digit number. Average area number of bedrooms is a 4-digit number. Area population is the 5-digit numbers. So kind of in principle, all these numbers are incomparable to each other. So in order to use the value of the coefficients of the model in order to rank the coefficients to say that, okay, this feature or this entry is the most important, we of course need to normalize the data first. But we are not doing it here because, as we're going to see, that it's already performing well enough. But in the next example, we're going to do it. Okay, so why there's so many coefficients of the linear model? Is it not supposed? The number of the coefficients of the linear model is equal to the dimension of your input data. And what is the dimension of your input data? We have 1, 2, 3, 4, 5 x's. Yes, kind of like we have a 3,500 entries. Yes, 3,500 vectors, but each vector is the 5-dimensional. So, and that is why, yes, we get here 5 coefficients, each coefficient for its own column. Okay, so now let's run a little code which is going to do the following, which is going to investigate what is the relationship between each kind of the entry of our data set and price. So kind of to see what is important and what is not important. So when we get kind of the average income vs price, average house age vs price, average number of rooms vs price, average number of bedrooms vs price, and area population vs price. And essentially, I think we could clearly see that area income is the most skewed narrowish one, but all of them are related except average number of bedrooms vs price is the least important feature just by judging by this figure. Yes, because you have 2 bedrooms and you have a wide range, 3 bedrooms, and you have a similar range. Okay, it's a little bit larger, but it's larger up and down. And the same thing about the other features. The other. Yes, we cannot make a conclusion on importance of the features based on the value of the coefficients in this example. That is absolutely correct because yes, yeah, the only conclusion whether the variable have positive or negative effect. Yeah, thank you. So, but the value of the coefficient doesn't have too much meaning because the data is not normalized. If we normalize the data, in that case, the value of the coefficients will be really correspond to the ranking. So we can say, okay, which is the most important, which is the least important entry. Okay, so now finally we can get some numbers for prediction. So we can calculate R squared, and I just remind you that R squared, and this is on the, okay, sorry, what I need to tell you first, how to predict. So we take our linear model after we've done fit, so kind of like the crucial steps, sorry. We've done fit, X train, Y train, and now we're doing predict of the X train. So we're just looking on what is the performance on the training data. So, and from the scikit metric, we can calculate, R2 score, and we get it. Okay, good. And if you remember, R2 score was from 0 to 1, and 1 is the best possible R2 score. So we're quite close to 1. And we can also do, now we can, because now we just predicted the performance of the training data. Now we can predict performance of the test data. So let's first see, let's do predictions. Yeah. So again, LM predicts, but now X tests. So this will be predictions on unseen data. And we can check that, that all is good in the sense like, okay, it's also array or the list of numbers, and the size is as it's supposed to be. And what we can do now, before we go, we can just compare in the predictions and in the test how they are related to each other. So actual with predicted house price. So we just need to plot a scatter plot, which I assume that you've seen last week in the matplotlib. Yeah. Between the Y tests and Y predicted. Yes, so predictions is predicted on an X test. And if we get a perfect agreement, we will get a straight line, Y is equal to X. And we see we're not too bad. We are in principle, there is a little bit of noise, but taking into account that we literally haven't done anything to our data set, we haven't done no normalization, no regularization, nothing, no experiments. And even without that, we get a pretty good, a little fetish, but, Y is equal to X line. And of course, we can calculate the formal indicators. So we can calculate mean absolute value, mean squared error. This is just as an example that, there is a whole bunch of these metrics within a scikit-learn. But again, you see, because our data is not normalized, these numbers seems to be out of the bound. But if we calculate R2, because R2 is the ratio, 1 minus ratio, it's a little bit more normalized. So we get that on the test data, we get 0.15, which is not bad. So because on the training data, it was 0.19 or 92, 0.92, and this is 0.915. So it's good enough. And that is why, that is why we're not doing all of these tricks with the normalization, regularization, because without that, the data set is so simple so that it's performing well enough. Okay, so now what we can do here. So kind of from here on, now how it's called, the interesting part starts for those who wanted to do a little bit of experiments. So here we've seen, so when we've seen that how each column is correlated with the price in the predicted. So we've seen that the number of rooms or number of bedrooms is rather irrelevant. And the question is, okay, if we drop it, what will happen to the performance? So we can create an extra train and test, we can call them X train 1, X test 1, where we just drop this column along the axis 1 because it's a column. If it was axis 0, it's a row, but of course, it will give us mistake because there is no row like that, but we need to indicate the axis. Okay, so we drop it. Now we can build a new model again, LM1, linear regression, fit, X train Y trained, the same Ys, predict, and we can get new list of coefficients, intercept terms, betas, and we can calculate the okay, so this is the score on the training data, and now we can also do the score on the prediction data, and we've seen that by dropping this column, essentially nothing have changed, at least from the point of these metrics. So as the R2 score was 9.19 on the training data and 9.15 on the test data, it's remained exactly there. So it's mean that from this point of view, it's really irrelevant column, or if it's changed something, we're not detecting that. Okay, so what else can you do with this notebook if you are willing to? And I encourage you, you can normalize the data. And scikit-learn have a set of normalization. And so we just go to the scikit-learn. Scikit-learn, scalars, standard scale. Okay, so it's a part of the pre-processing. And standard scalar is, yes, it's exactly doing that, yes. So that's what needs to be done. For example, so if we apply a standard scalar to the data, to the trained data, and afterwards we apply the same transform to the test data, we can see how it works and whether it's increased precision or not. But also in that case, if you do that, after you train your model, the coefficients suddenly are now will have a little bit more meaning, because now all your entries of your data set will have the same order of magnitude, because they'll be all taken from the Gaussian random variable with the mean 0 and the variance 1. Okay? Should you run removal of each individual column and return the calculation to see how much weight each column has? You can try, but you see kind of like it's much better to normalize the data and see the ranking of the coefficients. And to see the better result in this particular case, you need to normalize the data and add the regularization, because in the moment when you add in regularization, you begin to favor very small betas. And so suddenly you begin to kick out unnecessary things. So I wouldn't be surprised if we add here regularization, L2 or L1, we're going to see that, the column which was corresponding to the average number of bedrooms will have a very, very small coefficient. And to remove columns one by one, it's a little bit also difficult thing in the sense like we can remove column, but you don't know which column to remove. And so you need to take all possible combinations of columns. So it's really not worthwhile. So I suggest that, yes, it's better if you want to do something with this notebook, just normalize the data using the scikit-learn preprocessing tool and using the standard scalar and see what the result. And if everybody is happy with this notebook, we can go to the fancier one. In this case, yes, today we'll finish only with the two notebooks. Do you want to try a standard scaler by yourselves and tell me what is happening? Or should I move to the next one? Is it? Is it the break time? I don't think so, but you know, if you want to take a break, I don't know. To kill it? Yes.
Yes, Prof, we are due for a break now at 3.
Okay, wonderful. So we can have a break, and those who wants to work, they can try to do a standard scalar. And those who need a break, they can have a break. Okay,
Yes,
I'll see you in
so
15 minutes.
yeah, in 15 minutes.